Here we go. Last two sets of notes for the semester. They look long. This one's 3 pages. Assignment 17 is 4 pages. However, it's mostly because there are some larger graphs here, so it's really not that much. It is, however, just a hodgepodge of graphing stuff that normally would be an entire unit of its own. We go into a lot of detail, but we're just going to try to hit the highlights, so at least you've heard some of these terms before. You kind of know what they're talking about. You're a little familiar with it. So we're going to talk about finding roots or solutions from the graph, what those actually are, how to find them if we are given a graph, how to find y-intercepts of polynomials. That should be a review because we did it already with quadratics, but we're going to do it again with polynomials. We're going to talk about relative extrema, what that means, the different types, how to find it. And then we're going to do odd and even. So odd and even refers to both a function and a degree, or the graph. Okay. So the first thing is, what are all of the real solutions of a function when it's given to you? You're not going to have to find them this year from a function, but you are going to need to know what that is asking and how to find it if you're given a graph. So solutions are roots. The solutions when f of x equals 0 are the roots or the x-intercepts of the graph. So this is a super easy one to do as long as you're familiar with the vocabulary. As long as you know when they ask you for those solutions, what they're really asking are, what are the x-intercepts? So anywhere that it touches the x-axis. So it touches or crosses. Right here at -8.
Insects have 3 body parts. The body parts
right here
are the head,
at -1.
And the OddEven.
And then one last one right here at +1.
Insects have 6 legs.
So why don't you go ahead and B and see, can you find the solutions for B?
Some insects feel, smell, and hear and taste.
Okay, so it has one right here at 0. And then the only other time it intersects the x-axis is right here at 6. Now, one thing that we're going to talk about a little bit later, I don't think it shows up here, but when it hits the graph and doesn't pass through, it turns and goes back. That's actually called a bounce. And it means that that number is a solution more than one time. So -8 would actually be a solution more than one time. And I'll show you, I think it's in lesson 17 where that shows up. Yeah, it is, where that shows up again. And then here's another one. See how it hits the x-axis and then turns and goes in the other direction, as opposed to this one where it goes just across. So this is called a bounce. There's also something where it does this like little wiggle through, but that one doesn't show up this year. So this is a bounce, which means that 0 would be a solution more than once. They don't make you, I don't know. I don't think in Delta they make you write the 0 more than one time. I think they just have you write it once. I should double check that afterwards and address it in class though. Okay, so a review of finding y-intercepts. Find the y-coordinate, only the y-coordinate of the y-intercept of the polynomial function defined below. So to find a y-intercept, or any intercept really, you substitute 0 in for the other variable. So if we're trying to find y, we're going to substitute 0 in for all of the x's.
Wait, no.
So f of x, which is like your y, equals -7 minus 3 times, we're going to put a 0 in for that x, plus 6 times, we're going to put a 0 in for x, plus we're going to put a 0 in for x. So that is 0, that is 0, that is 0, and you just get 7. So again, pause the video and try B. So we're finding the y coordinate of the y-intercept. So we're going to substitute 0 in for x. Okay, so f of x, that's like your y. That's function notation, but that's like your y equals 0 times 0 minus 3 times 3 times 0 plus 4. So we get y equals 0 times negative 3. That's 0 plus 4 is 4. So 0 times anything is just 0. The next thing is relative extrema. So extreme values or relative extrema, those are the tops and the bottoms of all of the bumps. So let's see if we can get a good one here. Relative extrema are these points right here. So A and B, not C, because C is just an x-intercept. C is a solution, but D is one. Anywhere where it's at the top of a peak, like a hill, or the bottom of a valley. Those are extreme values. So they could ask you 3 different things for this problem. They can ask you what the extreme values are. That would be all 3 of these. All 3 of those are extreme values. If they ask you for an extreme minimum, that means like the ones that are at the bottom, right? This point's at the bottom of that little curve, so that would be a minimum. D is at the bottom of that little curve, so that's a minimum. B up here is at the top, that's a maximum. So this is a relative min. This one is a relative min. And this one is a relative max. So read the question carefully, which of those 3 things they're asking for. I have chosen 2 of them to do examples of here. This first one asks for a relative minimum. So it says how many points on the graph. They don't even ask what they are, just how many are there. How many points on the graph represent a relative minimum? So how many points are at the bottom of a dip? So you have 1, there's 2, and 3. So there are 3 relative minimums. B and E are relative maximums. Want to try B? Pause the video and try B. How many extrema are there? Relative extrema means it could be a minimum or a maximum, like both together. So it has 1 relative minimum and 1 relative maximum. So there are 2 total relative extrema. Okay, this last part is where it starts to get a little, oh no, not this one. Sorry, next one. Odd and even functions. So I thought we had a highlighter. Do pay attention to the way, again, just the phrasing and the way that they ask this. So the odd and even functions, okay? And you're going to have to do it 2 different ways. One based on they're going to give you an equation. That's what these are. And then next we'll do it with a graph. So odd and even functions. It's based on the exponents, like total, not just one, the total exponents. If all of the exponents are odd, then the function is odd. Okay, if every single exponent is odd, then the function is odd. If every single exponent is even or 0, because that would count as an even one, the function is even. There is a longer definition where you test like negatives and you plug them in, but we're going to stick with this, okay? So if every single exponent's odd, it's odd. If every single exponent is even or 0, it is even. If it mixes them up, then it is neither. So for example, A, that's an even, right? The 2 is even, 6 is even, And 8 is a constant. The exponent would be 0, x to the 0. So even, and an exponent of 0. That means that this is even. Every exponent is either even or 0. For B, 5 is odd, 3 is odd. The exponent for x is 1. If it's not written there, it's automatically a 1. 1 is odd. So every one of those exponents is odd. That means that the function is odd. And the last one, 8, so that's like 8x to the 0, right? So that's 0, 5 is odd, and then 1 is odd. So we have 0, odd, and odd. That means that they're mixed, because 0 should be with the evens. So 0 is an even, and then I have an odd and an odd. That means that they're mixed, so it is neither. They have to all be the same, or it's a neither. So what that means in terms of a graph, let's skip down to this one first. We're going to talk about odd and even functions, which is what we were doing up there, but also odd and even degrees. So kind of two separate things. There we go. There's a highlighter. Okay. So let's do the function first, because that's what we were just talking about. Ooh, that's kind of funky, huh? So an odd or even function. This is a lot of work just to try to highlight this for you. Okay, so an odd or even function. An odd function is symmetric to the origin. So these are going to be, we're going to look at the graph and try to see what it looks like. So an odd function, which is what we were talking about up there, is symmetric to the origin. Symmetric to the origin means that if you turn your paper completely upside down, it will look exactly the same. So if you turn your paper, put a note, because sometimes symmetric to the origin, we forget what that is. Turn your paper upside down. It looks the same. So an example of this, we probably already have one down here, kind of. An example of this would be if we did a curve like that, where you flip it over and it still looks exactly the same. That is a symmetric to the origin. That would be an odd function. An even function I don't know why I did that. Sorry, I am a wreck. An even function is symmetric to the y-axis. So remember, the y-axis is up and down. If it's symmetric to the y-axis, then you'd be able to fold it in half, your piece of paper, in half along the y-axis, and both of these two sides would match. Okay, so that's odd or even for a function. The next part is odd or even degree. So remember, your degree is only the highest exponent. The degree is the largest exponent or power. Okay. So it is, the degree is odd if the two ends go in opposite directions. So for example, this is odd because this side goes up and this side goes down. It is even if both of your ends point in the same direction. So a parabola would be even. We'll go through some more in a second. So you have to determine two different things about the graph, two different odds or evens. It would have been kind of nice if they didn't both do odd or even, right? One for the degree and 1 for the function. So I'm going to shrink this a little bit so we can keep that chart on there while we look at this. Okay, so this first one, based on the degree, is this odd or even? So go up here, based on the degree. It is odd if the ends point in opposite directions. It is even if the ends point in the same direction. Well, both of our ends point down. They're going in the same direction, which means that our degree is even. The function, and it has to be odd or even. They either go in the same direction or they go in opposite directions. The function, though, just like up here, remember it could be odd, even, or neither. So the function can be odd, it can be even, or it can be neither. This graph is, if I turn it upside down, does it look exactly the same? No. All of a sudden it would look like a W instead of an M. So it's not odd. It is not symmetric to the origin. It is even if it's symmetric to the y-axis. So if I fold this piece of paper in half, right down the middle on that y-axis, would it match? Would it be the same on both sides? Yes. So this function is even. So the degree is even. Also, the function is even. Okay, so let's look at the next one. The degree. The ends of this graph go in opposite directions. One end goes up, one end goes down. The ends go in opposite directions. That means that the degree is odd. The function, if I turn the piece of paper exactly upside down, will it look exactly the same? It would not look the same because instead of crossing up above, if I turn it upside down, right, now it's all of a sudden going to go down here, like it would cross down here somewhere. So it is not symmetric to the origin. If I fold it in half on the y-axis, does it look exactly the same on both sides? No, it does not. So it is also not an even function. That means it is neither. You should see if you can pause it and try these other two. Okay, did you try them? Let's check and see how you did. This function, my ends go in opposite directions. That means my degree is odd. Odd is opposite. Opposite directions. One side points up, one side points down. They're opposite. That means it's odd. The function itself, if I turn it over, like you could actually turn your Chromebook over. Does it look exactly the same if you turn it over? Yes. That means it is symmetric to the origin, so the function is odd. Symmetric to origin. Okay, last one. These two ends point in the same direction. They're both going up. So if they're going the same direction, that is even. Does it have any symmetry? So if I turn my Chromebook over or turn the picture over, does it look exactly the same? Nope. It would be over here and pointing down, so it doesn't look exactly the same. So it's not odd. If I fold my piece of paper in half along the y-axis, does it match exactly on both sides? Nope. Doesn't match. Not symmetric to the y-axis, so it's not even. So it is neither.